This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 07. The Carnot cycle. The second law's theoretical ceiling. No real cycle beats it between two fixed reservoirs. Expect a question or two using the Carnot formula as a sanity check, and many more where it's the silent upper bound for Rankine, Brayton, and vapor compression. Here's the problem. A steam plant between a hot reservoir at 500 Celsius and a cold sink at 25 claims 100 megawatts from 200 megawatts of heat input. 3 parts. The theoretical maximum efficiency between those temperatures, whether the 50% claim is possible under the second law, and reversed into a heat pump between a 22-degree room and -5 outdoor air, the maximum COP. Concept. Carnot is 4 reversible processes, 2 isotherms, heat addition at TH and rejection at TC, connected by 2 reversible adiabatics. 2 principles. Every reversible cycle between the same reservoirs has the same efficiency, and no irreversible cycle can exceed it. Carnot isn't buildable. Finite rate heat transfer needs a finite temperature difference, and truly reversible devices don't exist. It's the ideal limit, a benchmark. Carnot on the TS diagram is a rectangle. Top edge at TH is heat addition. Bottom at TC is heat rejection. The sides isentropic. The enclosed area is net work per unit mass. Efficiency is net work over heat in, which simplifies to 1 minus TC over TH, provided both temperatures are absolute. All reversible cycles between 2 reservoirs trace this rectangle. Rankine, Brayton, and vapor compression lose efficiency because their real paths deviate from it. Setup. 3 Carnot forms. Heat engine, efficiency is 1 minus TC over TH. Refrigerator, COPR, is TC over TH minus TC. Heat from the cold space over work in. Heat pump, COPHP, is TH over TH minus TC. Heat to the hot space over work in. An identity for any cycle. Heat pump COP equals refrigerator COP plus 1. Absolute temperatures mandatory, Kelvin or Rankine. Celsius gives absurd answers, often efficiency above 1, which flags the error. Variable table. 2 temperatures, 3 modes. Heat engine. QH is heat in, W net work out. Refrigerator. QC is heat from the cold space, W is work in. Heat pump. QH is heat to the hot space, W is work in. Same reservoir temperatures throughout, only the arrow directions and goodness metric change. Forward. TH 500 Celsius, TC 25. Reversed heat pump, TH the 22-degree room, TC -5 outdoor air. Pattern recognition. Theoretical maximum efficiency, or reversible between 2 fixed temperatures, means Carnot. Is this process possible? Means compare the claimed efficiency to Carnot. COP of an ideal heat pump is TH over delta T. A Carnot refrigerator is TC over delta T. If a problem says real cycle, Carnot is still the silent upper bound. Compute it first, then solve the real cycle. Step 1. The Carnot ceiling. Convert to Kelvin, then efficiency is 1 minus TC over TH, about 61.4%. That's the ceiling. No real plant between those temperatures can beat it. Step 2. Test the claim. Claimed efficiency is work over heat in, 50%, at or below the Carnot ceiling of 61.4, so it's thermodynamically possible. For context, supercritical steam Rankine plants hit 40 to 45%. Combined cycle plants exceed 55. 50% is plausible for a very well-designed plant, not typical. Heat rejected is QH minus W net, 100 megawatts. Most exam questions on this pattern are rigged, so the claim fails the Carnot test. Step 3. The reversed-Carnot heat pump. Heat pump COP is TH over delta T, about 10.9. Refrigerator CRP is TC over delta T, 9.9. Identity check. Heat pump COP equals refrigerator COP plus 1, which confirms. Real heat pumps achieve COP around 3 to 5 here, about a third of the Carnot ceiling. The gap is mostly expansion valve irreversibility and compressor inefficiency. Final answers. Forward Carnot efficiency is 61.4%. The 50% claim is allowed, but aggressive for real steam Rankine. Reversed heat pump COP is 10.9 ideal versus 3 to 5 real. Always compare claimed efficiency to Carnot rigorously. Don't eyeball. Traps. 4 ways Carnot problems lose points. 1. Absolute temperatures in the formula. Celsius gives a meaningless answer, often above 1, which flags it. 2. Write COP formula for the device. Refrigerator has TC on top, heat pump TH. 3. Reversible isn't frictionless. It means an infinitesimal temperature difference across the boundary, so infinitely slow, not realizable at finite rate. 4. Carnot is almost never the cycle being run. It's the ceiling, and the real cycle always comes in lower. Quick recall. 3 formulas: efficiency for a heat engine, COP for a refrigerator, COP for a heat pump. Heat pump COP is always refrigerator COP plus 1. Absolute temperatures mandatory. Real values are always strictly below Carnot, and a universal check is real efficiency at or below Carnot between the same reservoirs. Remember one formula, 1 minus T sub C over T sub H, and you'll handle most Carnot questions. Next up, Topic 8, the Rankine cycle, the first real cycle of the course. Steam power plants, 4 devices, variable table solve. You'll see how much Rankine gives up versus the Carnot ceiling you just computed. Before then, ask yourself, with Carnot at 61%, what fraction can a real Rankine plant capture? You'll compute it exactly in Topic 8. PEPrepengine.com/beta. The Carnot cheat sheet, the worked problem PDF, and a 5-question quiz are attached to this video. If the course helps you, subscribe.
The full study guide, with every equation and common exam trap, is free at PEPrepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.